Definitely, definitely.
Okay. So I welcome all the participants for this day two, session three. Session expert for this session is Mr. Ishan Vyas. Mr. Ishan Vyas has completed his bachelor's in chemical engineering with a minors in material science from BITS Pilani, Hyderabad campus. During his engineering, he has primarily worked on carbon capture technology and biofuels, which can be used in place of conventional bandages. Since graduation, he has been working with CADFEM, and in last few years, he has worked with various industries, including mining, pharmaceutical, chemical, processing, industrial equipment, etc., and help them incorporate simulation technology in their product development. He likes working on problems which involve multiple physics simulations like CFD DEM, CFD FEA, simulation related to chemical and pharmaceutical industry is his basic area of interest. On behalf of Mechanical Engineering Department, ADIT, I welcome you, sir, and mic is handed over to you.
Yeah,
Please.
thanks a lot, Bala sir, for that introduction, and thank you all the faculty members and research scholars joining this session today. And as Bala sir already mentioned, that I will be talking about the role of chemical engineering, or sorry, role of CFD in chemical engineering. Okay, so I'm Ishan Vyas, and I'm working at CADFEM India as a regional technical lead, and I have experience mostly revolving around CFD and also discrete element method. Okay, so just to start with, what chemical or process industry segment wise is. If we talk about chemical industry, it is actually a really vast industry which comprises of many subcategories as well. Okay, so to start with a few subcategories, it would be bulk chemical, let's say, which are sold in the bulk market where the requirement is huge. Then there are specialty chemicals which are consumed in low quantity. Okay, but they are more expensive in nature. And then you have agricultural chemicals, which the name already suggests. Then there is the section for paint, petrochemicals, industrial gases, process equipment, and water treatment as well. And if we talk on the other hand about materials, which is also where you will also find a lot of chemical engineering principles and unit operations being implemented, then we would talk about these mining, cement, metal, resin, glass, rubber, and adhesive industry, right? So just to help us understand that, okay, this is because when sometimes when people think about chemical engineering, they only think about, okay, this is going to be uh, more about chemistry or understanding or building or making some type of chemicals, right? But there are other areas also where chemical engineering concepts are involved, and even chemical engineers also work on those areas. Okay, so if I again talk about what chemical companies manufacture, like, they manufacture basically high value product by processing gas, solids, or liquids, right? So we are taking some raw materials. Okay, we are adding value by doing some processes on this raw material and converting it to a final or intermediate product, which can be either used by the end consumer or the end customer, or it can be utilized by some intermediate company as well. Let's say some company might be making some chemical, let's say ethanol, very simple example, right? So they are making ethanol, and that ethanol can have many applications in various industries, right? So, and they can be making something like paint, which has a direct use for the end customer. So but basically what we are doing is that we are adding value to the raw materials which we have got by doing some processes which can be related to mixing. We can be separating, like, reacting some, like, reacting multiple components to get the desired products. We can be heating or cooling certain products to get the desired or raw materials to get the desired product. We might be distilling, which is, you might already know how it is done in various industries. Then transporting, a simple physical operation. And um, uh, and then we engineer a wide range of materials using all these processes as well. So when we talk about um, how chemical companies impact the whole manufacturing supply chain, or the whole manufacturing industries, there are a lot of chemicals which are used in various industries, let's say construction, motor vehicles, paper, electronics, transportation, or agriculture, right? So although these industries exist, like an independent industry, but they are supported by chemical industries or the chemical companies, which provide certain compounds which are raw material for these companies as well, right? So this basically gives us an idea about what are some subdivisions which I already spoke about, right? Basic chemicals, synthetic materials. We can talk about agricultural chemicals, paint, coatings, adhesives, cleaning preparations. There can be other miscellaneous chemical products, and also pharmaceutical and medicine manufacturing. So even in pharma and medicine, you would see a lot of chemical engineering applications. The reason is that the processes remain same. The unit operations or the unit processes, they remains the same. You might be mixing two components, let's say A and B, in a chemical company which is making, let's say, paints or uh, any other component for that matter, and you will see similar type of mixing operation happening in a pharmaceutical company as well, right? So that makes this industry a really vast or widespread industry as such. Okay, so what that brings us to is there are various segments. I will not read out every name here, but this is just to give you an idea of what all can we do when we think about chemical industry. And uh, these, till now I have talked about segments or product wise what we will do in a chemical industry, but we also can look at what kind of processes or equipments do we look at, right? So we will be definitely looking at mixing tanks. We require mixing in many applications. It can be blenders, it can be polymerizers, hydro hydrogenators, and crystallizer or fermenters as well. So these all will fall under the mixing tank category, and we will see how we can use CFD for these applications. Then there is definitely separation, where you would see cyclones, hydroclones, electrostatic precipitator, or magnetic or flotation type of separation techniques. So again, these techniques are again influenced by some or the other kind of fluid. Okay, right? So we are using some or the other type of fluid forces to kind of achieve this separation, or we are using let's say in some cases electrostatic or magnetic forces also to achieve the separation. So we'll see how CFD plays a good role in understanding more about these equipments, these processes, and help us troubleshoot or develop these kind of process, right? Then filtration is definitely one, where even filters like aquaguard, which we have for water filtration, so those also can be modeled using CFD. Then we have heat exchangers. It can be simple heat exchangers, which a simple example of heat exchanger is the geyser in our at our home, where it is just for heating up water. But we can leverage the capabilities which we have in CFD to model those kind of systems as well. Then definitely dryers. It can be fluidized bed dryers, ovens, or spray dryers, and powder handling equipments like conveyors, mixers, dryers, and size reduction equipments. So I just wanted to quickly go through what chemical industry stands for, and how vast this could be, right? So in this presentation, when I talk about CFD, I'm going to limit my presentation on three major topics. One, I will cover the gas liquid systems. So what that will do is, because we see a lot of gas liquid systems in the chemical industry, right? So that will help us understand from gas liquid system perspective, uh, how we can use CFD, what is the role of CFD in those processes in chemical engineering. Then I will also want to look at mixing um, problems per se. Okay, so what that will do is, because again mixing is an important phenomena, so that is the second topic I have chosen, and the third will be environmental pollution control. So some applications where we are focusing on environmental pollution control. Now that will be applicable to any company or any research work per se, right? So let's get into the first topic, which is simulation for gas liquid equipment. Right. So, what there, whenever we talk about gas liquid systems, there will be some simulation capabilities required to realize these benefits. So, those speak about multi-scale, multi-phase, multi-domain, and multi-physics simulation, which all you can actually find inside ANSYS. Okay, ANSYS is the tool which we use for these simulations at our company as well, right? So we will talk about bubble column, spray tower, cyclone separator, plate distillation column, pack distillation column, and trickle bed reactors as well. So, talking about the first type of equipment, which is the bubble column, right? So, if we talk about the normal engineering challenges which we will be facing when we are designing a bubble column, uh, first will be flow regime transition. So, if you have read a little bit about bubble columns, you will understand that when the bubbles are so bubble column is basically a column of filled with a particular liquid, and some gases are inserted from the bottom of the tank. Okay, so it can be used for certain reaction or leaching processes in the industry, right? So the purpose is that you are basically creating surfaces in the in the reactor, which is basically the surface area of the bubble, right? So that is going to help aid also some chemical reactions which you might be wanting to have in that bubble column. So these bubbles, when they are formed initially, right, they have a certain flow regime, and then they go under a transition, and their flow regime basically changes. Okay, the shape of the bubble is going to change. They might break into multiple bubbles, right? So all those, and depending on the flow rate of the gas from the bottom of the bubble column, the flow regime is going to change. So we need to get to the right flow regime, so that our requirement is satisfied with that. So we also want to understand the bubble side distribution. Okay, so that would involve understanding about bubble coalescence and also breakup. Okay, so those two will be our criteria. Then mass transfer and chemical reaction, which is the purpose of these bubble column reactor. So that is something which we want to understand in detail. And distributors and internals optimization. So there might be some baffles or some type of internal structures which will be there in the bubble column. So you want to optimize those structures so that you can get the flow regime or the type of reaction of which you desire. And again, scale up is another important point, because let's say you are able to achieve a particular flow regime inside a lab, but it is possible that it is going to get very difficult when you scale it up to a pilot scale or a plant scale. So that is also something which we want to look at. So When we talk about ANSYS capabilities, ANSYS has transient multi-species, multi-phase population balance model, and phase change AID, also reaction and turbulence model. So all that put together, like these models which are available, that can capture any type of flow regime and any reaction kinetics which you might be interested in, right? We can capture transient behavior of the flow, right? We can, when we say multi-species, we, if let's say the gas which you are inserting in the bubble column, that has multiple gases, let's say it is a mixture of CO2 and N2, I'm just taking a very rough example. So that we can take care of, and their diffusion into, let's say, the liquid and whatever it be, depending on your requirement. Then there is multi-phase flow. So this bubble column is a very standard example of a multi-phase system, right? So this is this is a gas and liquid system where there is an interface between gas and liquid. There are two phases, gas, one is the gas and the second is liquid. So you want to model the interface between these two fluids properly, so that you can predict the bubble diameter, bubble shape, and things like that, right? So there are multiple models inside ANSYS which takes care of the multi-phase flow as well. Then we also have phase change models if that is something which is happening in the system. So all these capabilities will help us simulate systems like these. Now, some of the outputs which we can get from doing such simulations is we can analyze gas hold up distribution and flow field distribution. So inside the reactor, you can see that here we are able to see what will be the bubbles, what will be the spread of the bubbles inside the bubble column reactor. So that can be understood, then determine bubble side distribution and rising velocity. So you can plot the rising velocity, average rising velocity of the bubbles, and you can plot, let's say, you can understand the bubble size distribution also. So that can give you an idea about how close the reactor will be to what your requirement is, because bubble size will change the surface area of contact, and surface area of contact will change the reaction rates. Right. So then we have also, we can analyze the mass transfer rate and reaction rate in the at the interface, and through the interface. Then optimize distribution and internals, which we already talked about, and design columns with proper height and diameter ratio. Right. So even when you're scaling up, you need to make sure that these are in place. The second application which I want to talk about is the spray tower, right? So this is again, there will be some engineering challenges which we'll face, like defining complex multi-scale problems, because in spray tower, the the tower is really huge, but the size of the droplet which will be formed inside the tower, that is going to be really small. So the length scales are really varying, right? There is one big spray tower, so the fluid flow or the turbulence which is going to happen is happening at a very large scale, and then you have these small droplets as well. So you need to capture those, both these phenomena properly. We want to be preventing wall deposition in the spray tower. We want we want a nozzle which is specifically designed for the formulation which we have, right? So a nozzle design will greatly impact what will be the droplet size distribution, and how the flow breakup is going to happen, what will be the spread of the spray and things like that. So that is something which we want to understand, and measuring the impact of moisture evaporation on the drying agent as well, right? Because in spray towers, sometimes we are going to dry the material. So that we can understand. Managing particle residence times in a hot environment, and determining droplet size distribution as well, which I said again is an important parameter here. So in CFD, specifically ANSYS CFD, we have discrete phase models, which can take care of the small droplets, right? So whenever you have smaller size droplets which will not, let's say, break up into more droplets, smaller droplets, and they will just flow with the air, or they will be just dependent on the turbulence which is happening around us for their flow behavior. So that is where we take the leverage of discrete phase model. Then volume of fluid model is also there, which can help us efficiently track this initial region which you see, right? So this is basically an outlet from the nozzle, and you see for a while it is like a stream of the liquid, right? It is not broken down into smaller pieces till now, in the initial first part. So for this initial part, we want to very accurately capture the interface between the fluid and the air, sorry, liquid and the air. So that is where VOF model will be helpful. Now, what ANSYS did was that they combined these two models so that in a single simulation, what will happen is that initially when let's say the liquid is in a single stream, and VOF will be the best option to model that. So for that region, VOF will be used. And as and when we see that, okay, the sheet is now breaking up, okay, breaking up into small droplets, or, bigger chunks of drops. So then we employ DPM as well, right? So that will take the advantage from both these methods and put it into a single simulation so that we can do this in the most accurate fashion, right? So what this can help us get is flow field visualization. We can understand something, we can see this kind of simulation or animation being done. What will be the cone angle for this spray, and also the air core, which is going to form maybe inside this jet itself. Then sheet formation, this initial part is what we call sheet formation. Then when what you see after this is basically sheet breakup, which will break into some ligaments, and then finally you see in this area we mostly see just the droplets. So all these can be visualized as well. Evaporation rate, if there is a phase change happening, if the temperature is high enough to evaporate this liquid, then that can also be captured. And temperature field visualization, if it is a cooling or a drying application. Then droplet size distribution, as I already spoke about. So moving on, the next equipment which I want to talk about is the cyclone separator. So in a cyclone separator, what do we want is that what challenges we usually face is that the particle size distribution has a wide range. So that leads to design difficulty in designing these equipments, because what we are trying to do in a cyclone separator is separate certain size of particles from the other size of particles, right? So that can if the range is really wide, then it will become difficult for us to design these type of equipments. Then we also want to predict the flow inside the cyclones or hydro cyclones, which is a challenging task, because more than often they are opaque. They are made of metal or some other material which is not transparent. So we are not able to understand what is happening inside the cyclone separator and how we can improve that. And since we are talking about particles hitting the walls of a equipment, so there will definitely be erosion and corrosion which will take place, right? So we want to avoid that when we are doing when we are designing these cyclone separators. So again, we have multi-phase models which can take care of these type of applications as well, and even erosion models which can help us understand the erosion rates on a particular wall, depending on the flow rates and the number of particles which are there in the system. So we can as an output we can actually predict the erosion rate as well. And in case we are designing a new system, we can also get the separating efficiency of that of this particular cyclone separator. Similarly, I will also talk about the plate distillation column. Um, so conventionally, these are done based on empirical design, like based on our experience in ideal flow models. So, but if you talk about the real case, they do not have the ideal behavior. Okay, there is channeling, recirculation, and stagnant zones, which you will find in the plates of the plate distillation column. Okay, so when we talk about few major unresolved problems, that is the flow behavior of a given design. So you want to understand if there is any channeling, any recirculation, or stagnation zones which are being created. Then we would want to understand the effect of flow pattern on tray performance. So, and also entrainment and absorption mechanism, which is going to affect the distillation efficiency as well. So, with the Euler multi-phase framework, we have AIAD model also implemented. Okay, so that will help us accurately track the flow behavior of liquids and gases inside this plate distillation column. And since evaporation and condensation of could be some of the phase change effects uh, which are going to happen in this place distillation column, so that can also be taken care of. And multi mass transfer mechanism, so there might be uh, a single component, but it is the mass transfer are, let's say in different regions like droplet region, free surface, and bubbly regime. So in those regions as well, we can check the mass transfer as a different parameter for all these regimes as well. So, what kind of example outputs? Flow wheel visualization is going to be a constant throughout the CFD domain, right? So we can visualize the flow field as such, and we can also get the dissolution mass transfer and dissolution rate prediction, which actually changes the way a distillation column will behave, right? The dissolution mass transfer is a really important parameter. So that can be understood, and prediction of pressure drop is also possible. So most of the design of a distillation column revolves around what pressure drop it is going to experience as well. Like that is one of the main parameter, and with the help of CFD, we can understand that. And yeah, so moving on, I will talk about the packed distillation column, which is very similar to the plate distill. Like the process remains the same. Okay, so we will see a lot of same let's say similar applications and engineering challenges here as well. So I'm not going to go into the details here, but it is just that you can also predict the residence time in case since in this cases we'll want to know the residence time, as the packing, like the way you have created the packing structure, this structure which is shown here, that will affect the residence time, and that in effect will um, um, affect the way your distillation is happening. Okay, so that's again something which is very similar to what we spoke about in the last slide, right? And trickle bed reactors, again, these are a little different reactors, because there is a bed of, let's say, catalytic material, or maybe even inert material in some cases, and you again have complex multi-phase flow happening here. Okay, and non-ideal behavior in terms of channeling, recirculation, and stagnant zone. Okay, so we can leverage again the multiphysics model, multi-phase models which are there inside ANSYS, and even porous medium model. In this case, porous media model will be very helpful. So what happens is, when you have very small gaps in a particular let's say reactor in this case, because you will be packing the reactor with a particular uh, a packing material which can be inert or reacting. So so they will form a complex structure of pores. Okay, so if you just go ahead and mesh this whole geometry, extract the fluid volume of from it, and then start meshing it, so it is going to take a lot of time and effort, and meshing such small gaps is not possible. So what we do is take a small section, we approximate what is what will be the uh, inertial losses which is going to happen when a fluid is passing through this particular bed. Okay, and then we will use the porous media model to incorporate that behavior. So basically this trickle bed is going to act as a barrier in one direction in a certain fashion, and in the other direction in a certain fashion. So that is what we are trying to evaluate here using the porous media model as well, right? So that's about trickle bed reactors, and that also concludes our first section, which is on the gas liquid type of flows, right? And so let's talk about the simulation of mixing equipment next. Okay, so in mixing equipment we can talk about multiple systems where mixing is done, let's say single phase mixing. And then there can be gas liquid systems and bioreactors, solid dissolution where a solid and a liquid component is involved, uh, intermeshing mixers where something like a planetary motion type of mixers, or where more than one agitators are involved. Then static mixers is definitely one of the categories, and clean in pace mixers as well. Then we'll also talk about the democratization and system level modeling in case of mixing applications. So uh, uh, the first case, which is for the single phase mixing. So in any of these mixing equipment, or any unit process for that matter, or unit operation for that matter, there will be scale up or scale down which will be required, right? So that is one of the challenges, because the hydrodynamics change a little, right? Or it can change to a good extent also sometimes when you are scaling up or scaling down the equipment. And in more than often when we are doing research, or we are doing something at lab, we do not have the equipments. Obviously we will not have equipments at plant scale. So that is when simulations can add a lot of value, that you have your system in the lab or experimental level, and that can be definitely validated using the simulation result. Then you can scale up the whole equipment inside the virtual environment or the CFD tool, and then you can understand how the hydrodynamics are going to change. Do I have to change the type of impeller when I go to a plant scale? Do I have to change the RPM of the impeller, and things like that? So that is something which we want to understand. Then residence time and blending time estimates can become a challenge in some cases. In some cases where the, let's say, um uh, the component is shear sensitive, we don't want to have a high shear flow being happening inside that equipment. So that is when we can also look at the shear rates um, uh, inside the mixer. Then we also can look at blending of non-Newtonian materials. Okay, so there are viscosity models which are available inside ANSYS that can impart non-Newtonian behavior to the liquids which we are using, right? So that being said, The capabilities which we have in ANSYS, again, it remains the same. We have multi-species, transient and steady state simulation. We can also do particulate flow modeling. So let's say if there is some small amount of ink or some powders which are being injected inside the mixer, those those can be modeled. And since complex rheological models which will represent the non-Newtonian flows as well, those can be incorporated using the inbuilt capabilities as well, right? So some of the important outputs which we can get is shear rate tracking and reporting, so that we are not exceeding the shear rate. Let's say in some cases where we might be working with some bacterias or some biological entities. So in those cases, we do not want to um, uh, we do not want to load them with a high shear rate. So that is where we can take advantage of CFD as well, right? So that being said, let's move on to the next part. Okay, so in gas liquid system and bioreactor, we have talked, I think in detail about gas liquid system. So I'm not going to go into all the details here, but um, we can again, limiting shear rate will be an important point in bioreactors, because we are dealing with entities which are more sensitive to shear rates. They are biological entities, so that is when we are concerned about the shear rate which we are getting inside the equipment as well. So we can again do a mass transfer analysis, bubble size distribution, shear rate prediction, and liquid and gas field visualization. So these are actually really helpful for any engineering design or development and research where we do not have the actual equipment also, but we can go ahead understanding so much about these equipments inside CFD itself. Then let's talk about solid dissolution or solid liquid systems, right? So scale up and scale down, as I said, will be a constant theme throughout this presentation. Solid suspension or cloud height prediction. So whenever we are mixing a solid and a liquid, uh, we want to predict what will be the um, uh, you know how is the solid going to suspend or mix with the liquid, right? And so we want to check the mass fraction of this solid across the mixer, because we want a homogeneous mixed system. And we want to predict how much time should I run my mixers or the blender, so that I get the desired product. Okay, so and in some system, when we are modeling crystallization, right? So we also want to track the crystal growth behavior. Okay, so in this case, I think all the capabilities which we will be using will remain same from ANSYS, as we earlier spoke about. Okay, but a few new things. Maybe we want to predict the cloud height for a single or dual system, so that can be done, and that will be beneficial in designing these equipments. And a dissolution rate prediction. So if this solid which we have added in the mixer, that is going to dissolve into the liquid, so we can define certain dissolution rates, and that can help us understand its behavior as well. So moving on, there can be intermeshing mixers, right? What they would typically look like is this, where two types of two blenders or two agitators are actually in a single equipment. Okay, so these are a lot of time also used for non-Newtonian materials. Okay, so that's one challenge. We need to capture the rheology of non-Newtonian materials. And then second, there is this motion is really complex, right? Like in this case is okay, it is still okay because they are rotating about an axis and also rotating about their own axis, revolving around a single axis and rotating about their own axis. So that's fine, but these can get really complicated, and that is something which we would want to model out. Example outcomes which we can get is verification of impeller motion. So uh, s- uh, we want to check if the impeller motion which we are using, that is giving us the required results or not. Okay, so that is one. Then flow visualization, as I already talked about, that will be a common theme here. Okay, and also in case of dispersive mixing, which we are talking about, let's say of small solid particles or something like an ink, that can be understood the behavior of ink flow inside the equipment. Okay. In case of static mixer, uh, more than often a size is a constraint here, right? So you want to optimize the size according to the target which we have, or the requirement which we have. Then a lot of energy, static mixers sometimes consume a lot of energy. So we would want to, and an energy is going to be dependent on the pressure drop which we have, right? So we would want to minimize the pressure drop so that we can operate these mixers in the minimum amount of energy which we can use. And then since it is not so dynamic in nature compared to other mixers, if there is some reaction happening, there can be some uh, temperatures can increase throughout the reactor. So that is again something which we want to take care of. So understanding all these behavior and challenges, that can again we can leverage the help of CFD and understand what will be the concentration variation along the static mixer. It can be in radial or axial directions. Then shear rate tracking and reporting, we can get the local temperatures, like unlike experiments where we will be able to get temperatures only at certain locations where we put the thermocouple. But in case of a CFD simulation, we'll be able to get the distribution of temperature uh, across the static mixer itself, right? Um we can also look at what will be the interaction of this static mixer with the upstream or downstream equipment. So that can help us understand the whole picture about our set of equipments which we are dealing with. So again, when we talk about clean in pace mixers or mixing technology, where there we want to ensure sufficient and consistent cleaning process. Okay, so whenever we have any mixers, we will have um, sometimes inbuilt cleaning equipments as well. So we want to sometimes in case of pharma, that becomes really important, right? That you want to clean the mixer after a particular product has been made, for the next batch or next trials, right? So we want to minimize the cleaning time, minimize cleaning agent use, and minimize power consumption. So when we want to minimize cleaning time, okay, so that we can understand when we do CFD, we will be able to understand, you know, what how much time does the liquid is taking to spread across all the parts of the mixer, because again, these mixers might be in most cases it will be opaque and closed system, so you cannot actually look inside it. But using CFD, you will be able to do that, so you will be able to predict, okay, this is the amount of time which I need for the cleaning process. Then designing the nozzle or the spraying system or whatever system you're using to inject the cleaning agent here, we can also minimize the cleaning agent use. during this cleaning process, right? So again, we will be using the multi-phase capabilities here as well. So in most of the chemical engineering related applications, you are going to use multi-phase applications, because in general, applications, the real world problems are multi-phase. Like even if you look at a simple pump, right? A pump is also a multi-phase problem or a multi-phase simulation where you are looking at cavitation. But in chemical engineering, you're usually mixing or processing different components together. So that is why we use multi-phase flows very extensively, right? So again, in this case, we will also be able to understand the effect of nozzle design, as we also talked about how ANSYS can help us do a VOF to DPM conversion as well. Now, ANSYS has also been working on democratization of CFD or other simulation technologies as well. What that means is that it is a perception in general that simulation tools are used by, sometimes like experts who have learned the tool or did some research or coursework on that. But ANSYS has introduced uh, tools which can help us bypass that. Okay, if you have the domain knowledge, so if that is enough, you don't necessarily need to have a lot of tool knowledge to implement CFD. Okay, so then we are also looking at system level modeling, like where you are using reduced order model. So in case of, let's say, simulation of a battery thermal simulation, right? So battery thermal simulations are really complex in nature sometimes, because the meshing which you will be creating, that is going to be again a high number. The reason being that some gaps in the whole battery will be really small, so you will end up creating small mesh elements to capture that feature. So so what that does is that it creates it first it becomes difficult sometimes to converge those kind of simulations as well, and it takes a lot of time to simulate those cases. So that is why reduced order model has also been introduced inside ANSYS. So what that does is, this is similar to what you can call machine learning. It is not exactly machine learning, but it is similar to that. What we are doing is that we are taking certain sets of CFD simulations which are done on our equipment. We feed it to, let's say, an algorithm which will create a reduced order model, let's say, for this particular problem. And then whatever changes you want to do in the future, let's say you created a reduced order model for a mixer. So you did it for RPM, let's say, 200, 400, 600, and 700 RPM values for the mixer, and you created a reduced order model. And maybe this simulation which you do in 3D CFD, that is taking you, let's say, 6 hours of runtime. But if you create a reduced order model using these four data points, the next data point which you want to create for, let's say, 1000 RPM, that can be created in a few seconds using the reduced order model. And the accuracy is actually really close to what we get using CFD, 3D CFD, right? So again, ANSYS has also introduced an mixing wizard, which can help us streamline the process of doing the whole mixing process, or setting up a simulation for a mixing process as well, right? So this was all about the mixing equipment which I wanted to speak. Okay, so the last topic today will be the simulation of environmental pollution, simulation for environmental pollution control industry or research. So here, what we are typically looking at is we want to tune the combustion process. So we want to tune the combustion process such that the pollutants are minimized, right? We want to include emission reduction technologies which can help us meet the norms, and also decrease the amount of pollutants we are sending into the environment. Then exhaust gas quality control is something which we want to do in effluent water quality control. So when we talk about tuning the combustion process, the devices are usually complex to design, right? We might be talking about any, some combustion chambers, which we can be talking about any heaters which are using combustion as a source of for their heating requirement and things like that. So, and we need some measures to reduce the NOx, and but that can actually increase the CO emissions if we take those measures to reduce the NOx. And there can be operational and maintenance issues also, which we face continuously with these kind of combustion processes. So what ANSYS does is it has complete solution for furnace, reformers, boilers, and gas turbines, and it combines the combustion modeling capabilities for all these configurations. So there are dedicated fuel models which are available. So depending on what fuel you are using, you will have the set of reaction and reaction rates available for you. So you don't have to feed in all the data about the reaction kinetics, that is already available. And using the the robust heat transfer models and also combustion models, we can predict or we can design the combustion system which are adhering to the regulations. We can also as usual we can gain insight into flow physics and pollutant levels. So we can help us, like, instead of using a single burner, we might be using multiple burners instead of that. And we can check for different fuel composition, fuel air ratios, so that we get the least polluting system, but that also should specify our requirement, right? And we can also reduce dependency on testing with this. And also testing is really complicated when we are looking at any combustion system, because measuring any data becomes a challenge. There might be some losses, like predicting the exact amount of SOx or NOx which are coming out of a particular system can be again challenging and time consuming as well. So CFD can help in these areas as well. Then emission reduction technologies, right? We face challenges like poor mixing of reductants in emission reduction systems. So if the reductant or let's say in a selective catalytic reduction system is not mixed properly, then it is not going to help us reduce the emissions according to our requirement. So that is one. Then more than often the catalysts are plugged. Okay, so that leads to a reduction in the emission which we can capture. And there will be thermal stresses definitely between catalyst beds, right? Because they might be operating at high temperature. So that's what we also want to avoid. And ANSYS capabilities which will be helpful here is again spray and atomization. So understanding the spray behavior, droplet size, and droplet distribution, that can help us understand these injection characteristics and help us optimize that. We can also understand urea solidification and decomposition, because we have phase change models implemented inside ANSYS. Then there is definitely thermal stresses which we can capture, because ANSYS has a single platform for coupling various physics simulations as well. Like you can couple CFD simulations with FEA, you can couple CFD with electromagnetics also, and so on. So that would help us get the temperature distribution in a catalytic reducing system, and import those temperature distribution to the FEA tool, so that we can understand the thermal stresses which will be generated in this. Okay, so then also designing and retrofit to improve poorly performing emission. reduction units is what we can get as an output, right? So if we know that a particular system is not working, before we actually retrofit something on that equipment using empirical correlations or thumb rules, we can test it using ANSYS CFD or CFD in general for that matter, right? We can gain some more insight into overall system performance. So that is definitely there with any CFD simulation or any simulation for that matter. You definitely get more insights into what is happening inside your system or inside your equipment. Then we can also, since we are able to make these changes so quickly and also do it without a lot of spending a lot of time and money on building physical prototypes, we can deliver products which are adhering to the regulations as well, right? Now, when we talk about exhaust gas quality control, usually these equipments or components which are made, they have a short life, okay, and they have to be cleaned very frequently because exhaust gas contains those particulate matter. If they are not removed from the system, then the efficiency of the system drops very rapidly. Okay, then in most cases we found uneven flow distribution, which again leads to, let's say, a deposition of particulate matter in a particular location, and uneven loading of baghouse filters and electrostatic precipitator, which can again lead to an inefficient quality control which we are doing. So for ANSYS, we have validated models for cyclones, electrostatic precipitator, scrubbers, and back filters. So that gives us confidence that okay, whatever turbulence models or other models which I'm going to use, that is going to be that is well validated for the applications which I am looking at, right? Then what kind of outputs which we can get from here is we can determine the expected loadings prior to the field implementation. So if we know that this is the mass flow rate of the exhaust which is going to come, and this is the percentage of particles, let's say, present in them, so we can get the loadings prior to field implementation itself. And we can optimize our ducts and turning vanes so that there is no deposition in the ducts and other peripherals as well. And since we are taking care of all these things and making the process very efficient, the shutdowns number of shutdowns is going to drastically reduce, and also reduce cleaning frequency in turn. Then also the last, this probably the last slide, where I'll talk about the effluent water quality control. So typical engineering challenges which we'll face is we want to reduce the energy consumption, because if we spend a lot of energy in, uh, you know, uh, processing the effluent water, that could again mean that we are polluting the environment, right? So that we don't want to do. We want to increase efficiency of reactors, disinfection tanks, and coagulation and flocculation tanks as well, and improve residence time distribution in contact tanks as well. So to tackle these challenges, again, we have multi-phase models, which is going to be really handy in these cases, and reduced order model to for modeling ozonation in the reactors, right? Because ozonation is a complex set of reactions which is going to happen. So we don't want to have a detailed chemistry being modeled every time for that. Okay, so that's one. And what kind of benefits we can get out of these simulations is we can determine the equality or inequality of flow distribution among the lanes. So in general, we have multiple lanes which are there for these treatment plants, right? So because depending on flow paths like these, we can understand, or depending on the mass flow rates, we can understand what will be the difference or inequality in these in the flow rates here. And we can also determine the optimum number of primary tanks. and which will be required for treating a particular effluent, because we can understand the reaction rate, we can understand the residence time. So that will help us understand in turn the number of tanks which will be required. And since we can actually reduce the number of tanks required or the area which is required, we will minimize the land use as well, and in turn reducing the overall civil engineering cost. So this is what I had for today's presentation. I wanted to give everyone a glimpse of what a chemical engineer or chemical engineering would involve, and how CFD has been used in the past and still is being used in some of the cases. So since chemical engineering is a vast topic, and CFD is also again a really vast topic, so it is difficult to cover all the areas in a single presentation. But yeah, so I focused on these three topics. If you have any questions, I will be happy to answer right now.
So I request participants to ask your questions and queries. Ishan sir, can you tell us regarding a particular case study which might you have undergone as a project, or maybe a particular feature of the software which is being developed by your agency?
Yes. Let me check if I can quickly pull up some case study here. Meanwhile, if you have any other question while I
Of course.
pull up some case studies.
We have maintained this practice that, let us say, if any participants wants to ask any question, they may contact us, send those queries to me on my mail ID, and I'll convey the same to the expert, and maybe expert can answer over there also.
Yes. Please feel free to get in touch with us. We'll be happy to answer any queries at later point as well. Right. So that won't be a problem. So I do have a case study. Let's say I can project it just a second. Like, there will be multiple case studies. I just did not have something ready as of now. So
That is fine. If you can share one, it's okay.
mm.
Or,
so I hope my screen is visible.
yes, sir, it is. Please
Yeah.
carry on.
So this is a little old case study, I would say, but this was done with a major chemical company, right? And they had certain problems with a few of their equipments, right? And in particular, they were working on fluid catalytic cracking. Okay, and they they wanted to optimize their process so that they are able to reduce the energy consumption and also make this equipment more efficient. Okay, so they used CFD for this. They did the combustion analysis also, like flame tracking in this process. As you can see that you know there are two cases which are also projected here with different diameters of the pipes which are used. So the max temperatures are changing. So this kind of study where you could understand just by virtual validation what kind of effect a particular change is going to happen, that can help us a lot. And these changes which we have to make, right, these are very expensive if we have to make it at a plant scale, right? So that is why people have been using CFD in the chemical industry also for doing such calculations or changes before they go into uh, the 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 physical prototyping. So I can also share this case study over an email to you, sir, Bala sir. So maybe if possible, you can forward it to the participants for
Yes,
their
sir, of
perusal.
course. And if you don't mind, please share your presentation too, so that I can send the same to the participants, and which can
Yes,
benefit them.
definitely, definitely.
So, as there are no more further questions right now, so on behalf of Mechanical Engineering Department, A.D. Patel Institute of Technology, a constituent engineering college under CVM University, I would like to thank Mr. Ishan Vyas for his detailed presentation and uh, the way he touched the area of chemical engineering and chemical equipments, as well as automobile emission point. Thank you so much, sir, for sparing your valuable time and important information with us.
Thanks a lot, Bala sir, for arranging this, and to your institute as well for having me here. And please feel free to drop any questions at a later point as well. Yeah,
Of course, sir, and we'll stay in touch. Thank you so much. Have a nice day.
thank you. Thank you, everyone, for joining this session.